Waveguides Attenuation series on microwave engineering, lecture number 1.61. In the present module, the focus is on the attenuation the wave undergoes while traveling through the waveguide. It is called dissipative attenuation. In addition to dissipative attenuation, another type of attenuation also exists in case of waveguides is called reflective attenuation. In the present session, we try to understand the origin and also we try to find out methods by which we can reduce the attenuation. Now, let us move further. Attenuation refers to reduction in signal strength as it travels from one point to another point. The term attenuation is related to gain. Gain refers to output by input, whereas attenuation refers to input to output ratio. Basically, it measures reduction, fall in signal strength as it travels from one point to another point in the medium. It arises mainly in the waveguides from the dissipation of signal due to conductor losses and dielectric losses. The first one is due to presence of imperfect conductors and the second one is due to imperfect dielectrics. A perfect conductor is one for which conductivity is infinity and a perfect dielectric is one for which conductivity is zero. Usually the contribution from both together called dissipative attenuation is very small. Radiation into space always is a source of attenuation, but in guiding systems under concentration is absent. Another type of attenuation also exists in waveguides. It is called reflective one. It comes into being when signal of smaller frequency tries to enter into the guide. This one reflective attenuation is huge. Signal is simply reflected back without any further transmission. Now here a brief comparison between dissipative attenuation and reflective attenuation is provided. Dissipative attenuation has two components. One is dielectric losses and another is conductor losses. The first one is due to non-zero conductivity of the hollow region and the second one is due to non-infinite or finite conductivity of the guiding plates or walls. Reflective attenuation comes into being when frequency is less than cutoff value or wavelength is more than cutoff wavelength. Magnitude wise, it is enormously low when compared to dissipative attenuation. Reflective attenuation comes into being in case of non-TEM wave carrying systems, whereas dissipative attenuation is common to both TEM and non-TEM carrying systems. Here is shown somewhat idealized attenuation characteristic of waveguide. When frequency of the wave is less than cutoff value, Fc, then it attracts a huge amount of attenuation. It is called reflective attenuation. However, when frequency is more than cutoff value, wave travels able to travel through the waveguide, and while traveling, its amplitude keep on falling. However, this fall is very small. It is called dissipative attenuation. Here you can see comparing reflective attenuation, dissipative attenuation is negligibly small. In this particular tabular form, reflective attenuation, dissipative attenuation. For these two, expressions are provided along with a comparison type of characteristics of both. The attenuation constant due to reflective attenuation, alpha bar, is equal to 54.6 by lambda c square root of 1 minus lambda c by lambda naught whole square. This is in decibels dB per meter. It comes into being when frequency is small compared to Fc. Amount wise, it is huge. When it comes to dissipative attenuation, units are nepers per meter. It has two components, two parts. One is due to dielectric losses, that is due to imperfect dielectric that is there in the hollow region. Another component is due to imperfect conductor walls, that is conductivity of the walls being finite. The attenuation constant due to dielectric losses alpha d is given by beta square tan delta by 2 beta bar. Due to conductor losses, one can find out using a formula. This formula is power dissipated per unit length by 2 into power flow down the guide. This dissipative attenuation, it comes into being when frequency is more than fc. It is very low. This particular formula alpha c equal to dissipated power by power flow down proportional to dissipated per unit length by 2 into power flow down the waveguide. It is imported from transmission line theory. In the expressions for alpha, that is the attenuation constant, you can notice the presence of bar. Bar indicates here that these expressions are for non-TEM waves. Some information regarding reflective attenuation. When wavelength is more than cutoff wavelength, that is lambda is more than lambda c, or in terms of frequency, frequency is less than cutoff frequency, that is f is less than lambda c. The wave cannot enter into the guiding plates or waveguides. This behavior of the guiding system is taken into account by attributing large amount of attenuation called reflective attenuation to the guiding system. In dB, it can be shown very easily. The attenuation constant due to reflective attenuation is 54.6 by lambda c multiplied by 1 minus lambda c by lambda whole square. That is alpha is 54.6 by lambda c decibels per meter. The dielectric losses that take place due to energy absorption by the lossy hollow region in the guiding system, these losses give rise to certain amount of attenuation. The attenuation constant due to dielectric losses can be found as beta square tan delta by 2 beta bar. Beta means phase shift constant for TEM wave. Tan delta is loss tangent. Beta bar is phase shift constant along the guide length. It is in amperes per meter. The losses that takes place due to absorption by the imperfect conducting plates causes the wave to undergo considerable amount of attenuation. It can be found by using this particular formula, power dissipated per unit length by 2 twice power flow down the waveguide. This particular formula, it is imported from transmission line theory. So it is actually derived for TEM wave. That's why no bar is there over it alpha c, but it is being adapted to waveguides also, which are essentially non-TEM wave carrying systems. Now, how to find out alpha c for a rectangular waveguide, for a circular waveguide, or for a parallel plate waveguide? Normally what is done is power dissipated is found when wave is traveling to the guide. Certain amount of power gets dissipated in the walls of the guide. That power is calculated from Joule's law. I square R is the Joule's law, but this is circuit theory Joule's law. But here we are dealing with distributed parameter devices or circuits. So in place of R lumped element, the surface resistance comes into picture. In place of phi, J current density comes into picture. But idea is same. So using Joule's law, power dissipated is computed, and using Poynting theorem, power flow down the guide can be computed. What is Poynting theorem? E cross H gives you power flowing down, or half real E cross H conjugate gives average power that is flowing down the waveguide. Using that Poynting vector, power moving in the guide can be calculated. From the ratio, one can find out alpha c. For rectangular waveguides, the power lost per unit length is P lost is given by twice Rs by 2. Rs is surface resistance. Surface resistance of the walls of the guide. Here current must appear, but listen carefully. The current or current density, we are dealing with distributed parameter elements, distributed parameter circuits or devices. So current density comes into being, but current density and magnetic field, these two are related. So these are actually expressions for surface current density H by Hz. So this is it has two parts. This expression. One part is power dissipated in the side walls. First one. Second one is power dissipated in the broader walls. The first term indicates losses on the vertical walls, that is side walls. Second term represents dissipation on horizontal walls, that is broader walls. Power transmitted through the guide you can find out using E cross H complex conjugate. By applying that particular formula, you can find out P trans is half real part of Ex H conjugate minus Ey H conjugate dx dy. Of course, this can be put in a simpler form like half ZZ integral H trans square dx dy. This is conductor losses for circular waveguides. Here A is inner radius of the guide. Power lost per unit length is given by this formula. Rs by 2 H trans square integral is equal to Rs by 2 0 to 1 0 to 2 pi H square phi plus H square Z rho d phi d z. Power transmitted is again idea is same using Poynting theorem. Only difference from the previous expressions we encountered for rectangular waveguides is there things are in partition system, here things are in cylindrical system. In case of rectangular waveguides, after doing all the calculations for dominant mode, one can find alpha c is equal to Rs by b eta naught f multiplied by 1 plus 2b by a fc by f whole square Neffers per meter. Here f is a factor which is equal to square root of 1 minus fc by f whole square. Here a graph is shown attenuation that takes place in parallel plate guides. When frequency is below cutoff, you can see no wave is there except TEM wave inside the guide. As far as TEM wave is concerned, its attenuation is increasing with frequency. When it comes to TE waves or TM waves, they are attracting huge amount of attenuation near cutoff frequency. As frequency is increasing, the attenuation for TE waves is falling down, whereas for TEM waves, it is falling and then slowly rising. From this diagram, one can notice TM waves, they have minimum attenuation at a certain frequency. That frequency is equal to root 3 fc. In this diagram, the attenuation variation with frequency is shown. In A, rectangular waveguide, in B, circular waveguide, attenuation is portrayed for different modes TE, TM11, TM, TE11, TE20, TE10. TE10 means dominant mode. On the right hand side, you can find TE11, this is dominant mode, TM01, TE01 are also being shown on the right hand side. One can notice for all the modes in rectangular waveguides, the attenuation is decreasing and then rising. So at a particular frequency, it is assuming certain minimum value. When it comes to circular waveguide, here also, if we watch the curve for dominant mode, it is falling, and then it is rising and falling and rising. But for one mode, that is TE01, it is simply falling, no rise, with increase in frequency. When it comes to high power applications, power handling capability of the guide plays a significant role. How much power a waveguide can handle, it depends upon several factors. Those aspects we consider in the present slide. Maximum power that can be handled by a guide depends upon transverse guide dimensions and the dielectric filling the guide. Rectangular waveguide carries maximum amount of power Vmax when voltage across the broader walls is near to breakdown voltage, that is 3 megavolts per meter. Taking this breakdown voltage as standard or into consideration for calculation of maximum power that can be handled. For TE10 mode, dominant mode, maximum power that can be handled can be found as 597 or roughly it is 600 ABF. A is the dimensions, A and B are dimensions, inner dimensions of the rectangular waveguide. F is the factor already we come across several times, kilowatts. Here A and B are in cm, centimeters. In case of circular waveguide for a dominant mode TE11, maximum power that can be carried can be found as 1800 A square into F kilowatts. Here radius is in cm. So this is all as far as attenuation in waveguides and maximum power that can be handled by them. Enough.